The title of this note is Polar Systems, and your outcome is that you'll be able to find what are called the common points and the solutions of a system, both graphically and algebraically. We're actually going to focus in these notes just on the algebra, and we'll confirm it graphically in class. So how do I solve a polar system algebraically? So you've got some steps here. So a system of equations, if you think back to Algebra 1, you also looked at this in Algebra 2, you have two equations, you want to know where they intersect. You'd set them equal to each other. It's the same thing in polar. So you're going to set them equal to each other. Now because they're going to involve sines and cosines, you want to convert all of your trig ratios to the same ratio. So you're going to have to use your trig identities there. And then you're going to use any algebra skills you have, any inverse trig, to solve for theta, your variable. You do need to be alert that you're finding all your solutions in one period, and I'm going to show you an example of that. And then the last thing is you want to check the pole, because sometimes when you do this, the pole does not show up as a solution. So we're going to do two examples together. All right, so we're going to intersect r equals 3 sine theta and r equals radical 3 cosine theta. So before we even do any of the algebra, let's think of these graphically. 3 sine theta, that's a circle, a vertical circle, if I were to sketch it, that goes out to 3. And then radical 3 cosine theta is a horizontal circle that goes out to radical 3. So that's what the graph looks like. And we can see from the graph that it looks like two intersections. So we're going to solve for that algebraically. So step one, we're going to set those equations equal to each other. So 3 sine theta equals radical 3 cosine theta. Now step two, I can only have one trig ratio. So here I have sine and I have cosine. And I know that if I relate them to each other, sine divided by cosine equals tangent. That's one of my identities that I know. Sine divided by cosine is equivalent to tangent. So what I can do is I can divide both sides by cosine theta. And that'll give me 3 tangent theta equals radical 3. So now I want to get theta by itself. Let's divide both sides by 3. The tangent of theta equals radical 3 over 3. And then the last thing to get theta by itself is I'm going to take the inverse tangent on both sides, because inverse tangent and tangent will cancel out. So the inverse tangent of radical 3 over 3. So theta equals, and here I'm going to my unit circle. Okay, we got a couple tricks here. 3 and 3 make 6, so I'm looking for something with a denominator of 6. And this tangent is positive, so it could be in quadrant 1 or in quadrant 3. So I have pi over 6. And then in quadrant 3 we have 7 pi over 6. So these are the angles where those two graphs intersect. Remember, for polar graphs, our ordered pairs are r comma theta. So we have the two theta values. Now we need to figure out the r values. So r1 was 3 sine theta. Substituting in the first theta that we have, which is pi over 6. And then thinking about my unit circle, the sine of pi over 6 is 1/2. So the first solution is 3 over 2 pi over 6. And you could have plugged that into R2. You should get the same thing. Let's check that. So radical 3 cosine theta, plugging in pi over 6. The cosine of pi over 6 is radical 3 over 2. And then radical 3 times radical 3 is 3. So it works in both of them. All right, let's try the other theta value that we solved for, which was 7 pi over 6. So just so we don't get confused, I'm going to do that one in a different color. All right, so think about my unit circle, 7 pi over 6. The sine of 7 pi over 6 is negative 1/2. So my other solution is negative 3/2 7 pi over 6. If I were to plot these points, these are indeed the same point. And how do I know that? Because the r's are opposite, and these spokes are opposite. They're 180 degrees apart. So that's actually two different ways of finding the same point. So even though I found two theta values, I've actually only found one solution point. So step 4 is I need to check the pole. The pole is when r is 0. So I know that at the pole, the radius is 0. So my first equation was 3 sine theta, and I'm going to check the pole. This is step 4. And at the pole, the radius is 0. So I'm going to plug in 0 for r, and I'm going to work this backwards. Dividing both sides by 3. 0 divided by 3 is just 0. So thinking about my unit circle, what angles have a sine of 0? Remember, sine's your y-coordinate. So theta is 0 and pi. That's for R1. Now let me check for R2. R2, this is cosine. At the pole, the radius is 0. Dividing both sides by radical 3, I get that 0 equals cosine theta. The cosine of an angle is 0 at pi over 2 and 3 pi over 2. So what this is showing me is if I look back at the graph, it looks like those two graphs do meet at the pole. But notice that the first equation gets there at 0 and pi. The second equation gets there at pi over 2 and 3 pi over 2. So while the graphs do overlap at the pole, they don't get there at the same time. So the pole is what we call a common point, whereas the other point we had before is called a solution. So the difference between a common point and a solution is that a solution is when your two graphs intersect at the same time. So that's the solution. So the solution, they get there at the same time. The common point, the paths cross but not at the same time. So think of this like air traffic control. If these graphs represent airplanes, the paths of two different airplanes can intersect as long as the planes don't get there at the same time. Because if the planes get there at the same time, they will fly into each other. All right, let's look at another example. So here we have r equals 1 and r equals 2 sine 2 theta. So think about this graphically. This is a circle centered at the pole that goes out to 1. And this is a vertical rose with 4 petals that goes out to 2. So there's our two graphs, and we want to figure out where they intersect. So step 1, set them equal to each other. Lucky for us, this time there is only one trig ratio. It's a sine. So we're going to start solving for theta. So this is working from the outside in. We're going to divide by 2. Should be an equal sign there. 1/2 equals sine 2 theta. And then let's do inverse sine here. So you're asking yourself, for the left side, what angles on the unit circle have a sine of positive 1/2? And it's pi over 6 and 5 pi over 6. And then your last step to solve for theta is to divide by 2. Dividing by 2 is the same thing as multiplying by 1/2. These fractions are a little bit easier to manage. So there are 2 solutions for theta, but I hope you can see that there ought to be more than 2 solutions just by looking at the graph. And in fact there are, and it has to do with domain. So if we were going to graph 2 sine 2 theta, this is our b value, and remember the period is 2 pi over b. So that graph has a period of pi, which means that on the domain from 0 to 2 pi, it repeats twice. So we don't have all of our answers. So what we can do is we can go back to this step here. We know that pi over 6 equals 2 theta, but we can add 2 pi to that. So 2 whole pi's. And there we get another setup. Same thing here, we can add 2 whole pi's. The way I'm doing this quickly is 2 whole pi's cut up into 6 give me 12 over 6. And I'm adding the 12 and the 5. All right, and then same thing I did before, right here, multiplying by 1/2. So 13 pi over 6 equals theta, and 17 pi over 12, sorry, this should be 12. Forgot to multiply those denominators. Equals theta. If I'm not sure what to do here, I can try adding 2 pi again. So adding 12/6 more gives me 25/6. And then multiplying by 1/2, and I'm getting 25 pi over 12 equals theta. But I can tell that that's an extra solution because 2 pi, if I think of it in terms of twelfths, is 24 twelfths. So this has gone more than 2 pi. And in fact, if I subtract 2 pi from it, I get pi over 6, which is a solution that I already have. So I can stop here because this solution is more than 2 pi. And I'm just trying to find my solutions between 0 and 2 pi. So to recap, my theta values between 0 and 2 pi that I solve for right here. 13 pi over 12, 17 pi over 12, 1 pi over 12, and 5 pi over 12. So we're going to stop there. If you want to throw your trig identities, don't worry about memorizing these, but they will be helpful to have somewhere in your notes for simplifying some of these polar equations, especially the first 2. And then we're going to stop there.